Hello, and welcome to our new episode of the series People Should Know. I, Dr. Vaishnavi Tiwari, am your host for today's session. People Should Know is a series which has been launched by the Indian Youth Nuclear Society that aims at inviting leading experts to discuss about the facts and the details of nuclear industry in a manner that is comprehensible to the general public. For today's episode, we have with us Dr. Prabhat Kumar, who is an Emeritus Fellow and construction expert at the International Thermonuclear Experimental Reactor, or otherwise known as ITER facility in France. Dr. Kumar has been a part of various national and international nuclear establishments, such as the NPCIL, the DAE, IGCAR, as well as ITER. And if I remember correctly from our last interaction during the Being Informal with series episode with Dr. Anil Kakotkar, he is also the only person who is known to have the experience in all the reactor technologies that are presently in use in India. And today, he shall be discussing with us about the role of thermal fast fusion reactor technologies in India's energy security. Welcome, Dr. Kumar.
Thank you, Vaishnavi. Thank you, Indian Youth Nuclear Society, for inviting me. This is an opportunity to talk to general public and young generation. So I'm ready. If you have some questions, I'll try to respond.
Thank you, sir. So, to start off our discussion, can you please briefly tell our viewers about the history of India's nuclear energy production program? Sir.
Fascinating question, and the fascinating answer is going to be there. See, I have lived through this program, which was started, of course, in 1958, soon after India got independence, and Dr. Bhabha Pandit Nehru launched a stage program. Actually, it is stage program which was launched. Dr. Bhabha conceived the entire program, that is three-stage nuclear power program. It is very well known, not only within India, this is globally too. That three-stage means we have to have a closed fuel cycle, and we have to be self-reliant. We have to do everything of our own, be it research and development, be it industrial activities, be it reprocessing of the fuel fabrication, and everything. Now, how it happened? It was all built in on two focuses. Number one focus was research and development, and the second was nuclear energy production. So that's there was this organization to make nuclear energy. There was a large organization to undertake R&D program to cater this to this nuclear energy, and so many peripheral organizations to create a network of the capabilities which can support these two programs. Now, if I go, the whole thing was divided into three, parts. Number one, government sectors, which has R&D organizations, as well as some of the industrial activities. It has power sector, of course, which is Nuclear Power Corporation, Bhavani today, and then it has so many supporting organizations, of course, in both in industrial sector as well as government organizations. That is, for example, Nuclear Fuel Complex, Uranium Corporation of India Limited, etc., etc. They all support each other. They feed each other, and they have got their own expertise. And it was very slowly, but very systematically developed. And from that three-stage program, which was conceived by Dr. Bhabha, that will use natural uranium, which is available with us. That time when he had conceived, it was just available for 10,000 megawatts for 30 years. Of course, later UCIL had a lot of new finds, and we became much more independent on that one. Of course, we import a lot of fuel also, but our main emphasis was to use thorium. And if thorium which is world's one-third reserve, if that is to be used, then we have to first stage, that use of natural uranium, we have to convert to plutonium, have capability of extracting the plutonium, make mixed oxide fuel, that mixed oxide fuel along with the depleted uranium we have to use and produce more fissile material in the form of uranium 233, as the more and more plutonium, and then go to thorium and produce uranium that is uranium 233, and go ahead with the thorium U33 cycle. Now, it is very robust program, and it is amazing to see that even after almost, almost 60, 65 years before it was conceived, that is still going on. And there were many visionary and wizards who have led this department, and they have all carried on this program very systematically and built around this R&D and nuclear power program. And both today are very robust. R&D of India is very robust. BRC is a worldwide known organization, and IGCAR2 is a worldwide known organization. Similarly, RR CAT, BECC, they're all very important organizations which are carrying out an entire program. So I'm a witness to this thing, because when I joined the department on the year when Pokhran explosion was there, Pokhran 1, and then all the foreigners had walked out. India had to be completely self-reliant, even in production of the equipment. There was not, this much infrastructure built in the country. But then our seniors started working with industries, supported them, built machine for them, trained them in quality assurance, trained them in production, and then try to make every equipment, fuel and heavy water, everything within country to on accelerated pace. So this very fascinating history for nuclear power industry in India. Yes,
Absolutely.
you can.
And to think that the planning started so long back, it's a commendable job, I would say. Well, moving on to our next question. I've learned that you have had almost, in your 46 years of experience, you've been closely associated with a lot of major projects that are concerning the PHWR, the PWR, even BWR and fast reactors of India, as well as the fusion reactor technology. Could you tell us about some of the challenges that you faced in maybe the construction and the operation phases of these fission reactor technologies? And secondly, since fusion is relatively new, the fusion technology is relatively new, do you foresee any particular challenges when it comes to the operation phase of fusion reactors in India or maybe internationally as well? So,
Thank you, Vaishnavi, for this question. Yes, I had very satisfying professional career, so long and always with mega projects. I have seen things being built. Now, your question was that what are the challenges? Yes, such large programs, if they are taken up, they are never without hiccups. And as I said, that we started complete self-reliance almost from the time 1974 when there Pokhran explosion, and we had no international help in science, in technology, in equipment, rather many equipment for power reactors, Rajasthan and Madras, which were there in industries in other countries, and even in ships, some of them were returned back to those countries, and we didn't have we didn't have any access to those equipment, and we had to make ourselves. So the first thing was there that develop capabilities, industrial capabilities, so that we can make this equipment. Complete become self-reliant in heavy water and nuclear fuel. Now, the first hiccup which we had was that heavy water production didn't match the power production program which was there. And I remember in my very young age, when we used to design the nuclear power plant, we were told, don't use much heavy water, reduce the volume of the heavy water use, means reduce the length of the pipe, make things cramp, make things pipe smaller, and all whatever is possible, you do it. Now, of course, today from that time onwards, what a leap India has taken. What a massive production and lots of surplus heavy water production. So this starting phase is always very challenging. I also remember a time when we had lots of fuel shortage. Fuel which has to go as a feed in the reactor, that shortage was there, and the production capacity didn't match what was NPCIL was requiring as a to cater to the program. And with that one, now such a large program is there, and still fuel is never a problem, and that's the gain. Third thing is that sponge for the production of the fuel was to be produced by Uranium Corporation of India Limited. And this was always a problem. NFC was always having to begin with trouble of not getting adequate feed. And from that time onwards, so much, the job has been done by UCIL successfully. So much production of the fuel sponge has been done, and they kept on exploring and find out what are cheaper and cheaper and faster and efficient ways of converting this whatever excavated material to the sponge, which can be used by NFC. It all extremely fascinating. As far as nuclear power program is concerned, that also didn't match its own expectation. It was also, this department was conceiving something, but department cannot go of their own. They have to depend upon the government. There was a time, I remember, if it was, I think, 83 or so, when almost there was no program, no reactor was being sanctioned. Now, if this type of mismatch is there, both industries had problem, fuel production has problem, uranium corporation, because everybody has interdependence. They live on each other's money, and if nuclear program does not power program does not go, others cannot flourish. And in the meantime, department kept on increasing R&D facilities to take more and more program. And there were in the process lots of surplus was created everywhere, and but efficiencies were improved, skills were improved, and department became more and more stronger. But department never gave up. It produced IGCAR started. Indira Gandhi Center had advanced research to do advanced technology research for fast reactor, which was extremely vital for the secondary stage of the nuclear power program. In fact, the power program of India cannot sustain nuclear power program unless until we go ahead in a very successful and robust way with the fast reactor program. And there, first use, as I said, plutonium MOX fuel along with this depleted uranium, and at later stage move to thorium. That has to be there. So that's why IGCAR took up this particular responsibility, and they started working. And thorium, as far as thorium is concerned, BRC also had a parallel and very, very efficient R&D program for the thorium reactors. So as I said, that we didn't have, our journey was not smooth. There were lots of difficulties faced. Even first of its type technology, we had failure of end shield, leakage in the end shield, Calendry overpressure relief devices, moderator inlet diffuser failure, reactivity mechanism and shutdown system, some of the failures which has taken place. Of course, shutdown system failure has taken place only during pre-commissioning stage at Narora and not later. Steam generator failure. So when such type of failure comes, most of them are in the radioactive area, and they required extensive effort, mock-up training, and remote handling, and then take on this particular job. We had to do everything of our own, but the department had such a high commitment that everywhere we succeeded. And all this type of failure which has taken in the similar reactor elsewhere, including Canada, we did in much lesser effort, much less money, much lesser MENREM. MENREM is the terminology, of course, how much radiation dose has been taken by the people who were working on this thing, and much faster. And that's the capability of Indian, and that's the capability of India's nuclear power program and the Department of Atomic Energy and its units. Yeah.
Thank you, sir. Yeah, indeed. I mean, to carry out all these tasks is definitely it's going to be challenging because it's not like it's on a dummy scale or a small, short experimental scale that we're trying to do this effort. So, yeah, vigilance and being always up on your toes is important for sure. Well, if we see currently in India, we have about 22 nuclear power reactors that are up and functional. And one of the interesting things about the program is, like you said, it's a mix of different technologies. We have boiling water reactors as well as PHWRs and PWRs, and the PFBR, which is a fast reactor, first of its kind, which has been constructed in India. Now, apart from the main goal that we need these different technologies in for our three-stage power program. What do you think are the pros and cons for using such a mix of different reactor technologies for the Indian energy program?
Thank you very much for this question. This is a very important subject to see how a program is managed. You have to ultimately become self-reliant, as repeatedly I am using the word self-reliant in nuclear energy program. But how? See, when India became independence, industrial infrastructure was very less. R&D infrastructure was almost minimal. But Department of that time, Dr. Bhabha conceived a very large nuclear power program. How to go ahead? You have to learn. So, this whole program was not was aimed at how do we ultimately achieve our ambition of producing abundant energy resource which is there and which is a clean source of energy, go to that one. So first stage we had to learn. So for the learning, BRC launched 3 reactors, Jarlina, Purnima, and Cyrus, 3 major reactors. Development program, irradiation of the materials, try to see neutron effects, try to also produce isotope, and to do some public services and public benefit for the public. In addition to this thing, decision was taken to import reactor. This Tara put 2 units of pressurized boiling water reactor. Now, this was on a turnkey basis, was built by Bechtel and was contracted on then. Okay, I'll just this thing. So these particular reactors, when they came, they taught us how to build a reactor, how to do quality assurance program, how to do a safety program, and how to train manpower in operation, in commissioning, what care to be taken, what is cleanliness during construction, how to integrate civil works with other electromechanical work, and what is the backup infrastructure which is needed to run and operate a nuclear power program. It was a very great learning for the India. In addition, now, since our mainstay had to be the natural uranium use so that efficient use of uranium can be done, India launched a program with on the heavy water reactors. And Rajasthan 1, Rajasthan 2, Madras 1, Madras 2, these were all reactors started. It was started with Rajasthan 1 and 2. When this particular reactor was signed, then we had a deal, the department had a deal that it will be, this partial supply by them, partial supply by Indian, construction, lots of support will be done with the support of Indians. Now, fuel they will help, but ultimately they will also teach us for the fuel production. Also, they will support us in heavy water production program. And these were all, this was learning phase. So India's involvement right from design to construction, to commissioning and operation, that was all conceived by this reactor. And this reactor was made, Rajasthan one was made critical in 1972. But 74, with Pokhran explosion, the Canadians walked out, and so were all other countries. And then India did commissioning of Rajasthan 2, Madras 1, and Madras 2 of its own. Of course, Narora is completely Indian, was completely designed and fabricated on the Indian concept and Indian design. So it was very important for us to go ahead and develop this particular capability. But R&D for fast reactor was one of the most important program. And R&D full organization, this is R&D, well, IGCAR is one of the finest organizations I have seen. Of course, nobody can match BRC, but the IGCAR is a very, very great organization with very large equipment and great facilities, very capable persons to do the job. They designed this fast breeder reactor, PFBR. And to launch this particular reactor, a new company was formed that is called Bhavni. Bhavni was formed so that they can build this particular this reactor, because ultimately this is a NPCIL program. NPCIL R&D was done by BRC, and all other work was done by NPCIL. But here, the design and R&D was in the domain of IGCAR, and as far as construction was concerned, was in the domain of Bhavni. Bhavni also had a very, very capable team, very dedicated, very capable, and young team, and filled with lots of energy. Of course, they build reactor very, very effectively. During commissioning stage, of course, it can happen. First of its kind technology, everything first of its kind. So some difficulties may be faced, and some difficulty was faced. And they are commissioning, and I'm very sure very fast they will commissioning, because they have got a massive support from IGCAR and very large support from NPCIL and BRC, and that will also be successful. Is there any second part of your question, Vaishnavi, I forgot in this one?
Sorry.
No.
No, sir, it's just about the different pros and cons, yes.
So, there's pros and cons. When there are so many technologies, you have to have people capable of in all this technology, because they are different technology. Their control systems are different. Their maintenance requirement is different. Their total shutdown program, their refueling program is different. For example, boiling water, pressurized water reactor, they have to be shut down to replace the fuel. Online fueling is for pressurized heavy water reactor, and the online fueling program is going to be for PFBR. Of course, I forgot to tell you about India making launching a tie with Russia, and VVR reactor. 2 units, of course, are operating. 4 units, more units are under construction. I was associated right from beginning with the VVR program also. With so many technologies, we have to have many people to handle all this technology. There was a gap. Actually, there is a very important aspect of it, that once we have become self-reliant and robust, we have developed very robust fast breeder, the PFBR, heavy water reactor technology, and we can go ahead in a very long way. But then there we have to meet the energy gap between demand and supply. So demand and supply gap to be met, and that's how we have to have imported reactor. Russian reactors, VVRs, for that purpose, and whatever other discussions are going on with the various other countries to buy the reactor, is to bridge the gap between demand and supply of the power. We should support each technology, not only nuclear technology. We should also support, this other sources of energy, which are green energies, and that so that we can support each other, and then India's energy need can be always met. Okay.
Thank you, sir. Discussing about how the industry was built up, we've heard the names Bhavini, NPCIL, IGCAR, BRC, these organizations. We've heard the names so many times, but I'm sure there are also certain silent partners or certain silent industries which are, effectively contributing to this nuclear power program. So, can you tell us about some of these industries and particularly what role do they play in the nuclear power program, sir?
Yes, without industrial participation, nothing can happen. So ultimately, we have to have a three-dimensional equipment coming and getting installed somewhere, even if it is for uranium exploration and mining and sponge preparation or fuel fabrication or reactor construction or even for R&D. Industry's participation extremely important. As I said, industry was very, very weak when the trade embargo in 1974 started. But the quality assurance program the Department of Atomic Energy taught and brought to the industries was brought turnaround. And many Indian industries today are known globally and they are supplier globally to the various industries, including nuclear power industries. You want me to name some of them? If you want to name some of them, I can name. I will start with Bharat Heavy Electricals Limited, BHEL, which has been always very, very strong and great support. I must say Larsen Tubro. I must say Walchand Nagar Industries, Kirloskar Brothers, MTAR, and many more, because this. I will always risk omission if I take more name, because I must say many more were very important industry. They worked with us, produce very high quality program. For example, make can rotor pumps or make pump for circulation of the primary heat transport system, make heat exchangers, and make calendaria and shields, etc., etc. So they were all, and of course, power that power production, the turbine and its loop was also to be generated, and BHL, of course, always played a very major role on that one. So we have always reason to be very thankful to Indian industry. Without their help, we could have never succeeded. Lots of robotic tools were required. They were all conceived. Many of them were conceived, developed, manufactured, proved, tested by them. With, of course, and then we have deployed in the reactor very successfully.
Thank you, sir. You talked about the different, difficulties and challenges. Like you mentioned about the different accidents that we foresaw during this construction phase or operation phase early on, and things like that, and also about when you said that there was a gap in the, the demand and supply. So can you just maybe shed some light on a few more of such hiccups that India has faced during its journey? So
Well, construction phase accident, these are industrial accident issue. I must say that uh, Atomic Energy Regulatory Board has set up a separate unit which looks after the industrial safety of all the nuclear establishments within India, not which is not related to the nuclear operation. Nuclear operation they see very stringently, but very strictly they also see industrial safety. And our industrial safety norms and our industrial safety standards are much more stringent compared to any other industry in India. So even though it was not possible to always avoid accident, and some accidents have taken place, and in many nuclear establishments during construction, there was loss of time and even loss of some of the life. But if we compared with the general industry standard in the India, nuclear industry was always better, and we were always hammered by Atomic Energy Regulatory Board if we didn't perform well in industrial safety. They always wanted our standard to improve, even in civil construction, where the laborers used to come and lots of migratory laborers are there. Construction industry has got this typical issue of the migratory labor. You have to train large number of people and give very extensive training and ask them to work differently in our place compared to even contractors work differently in our place compared to other places. But during initial stages of operation, Also, we had lots of difficulties, and these difficulties were some of the failures. Unavoidable, of course, because you are developing technology of your own, you will take all care, but still there may be certain things which might not have been foreseen, and that may have its own difficulty. One of the end shield of Rajasthan Unit 1, they cracked, and that particular crack has taught it a lesson. We should have probably had a different material, or whatever in situ heat treatment was done should have not been done. So that was a lesson from us, and it was a very difficult job because it was a very high radiation field. It demanded that we do this maintenance. Maintenance was done, tools, procedures were developed in-house, completely in-house, and then this particular job was done successfully. Overpressure relief device that was done, and that was also remote handling. Then moderator inlet diffuser failure in Madras Unit 1 and 2. This particular thing, of course, Dr. Kapotkar has played a very major role in most of the places, including moderator inlet diffuser maintenance. He was overall in charge and responsible for this job. From there, we had to again do very high radiation jobs, cutting and removal, and then find a place where all this damaged portion could be kept inside the calendar, and even it can remain safe. So these were the job. See, we had during pre-commissioning, as I said earlier, also the failure of the shutdown systems during pre-operation phase, and when we're doing commissioning, and then it required certain change of the equipment and some little technology, and then that particular job also has been successfully done. So what happens that when we take up a program, there is always certain amount of hiccup will come, and we have to say how to develop tooling. Our capability lies in developing tooling, that not necessarily everything was conceived that this can happen inside the calendar vault. How the tool will go in various places, or inside Calendria, how these tools will be sent, how inspection gadgets will go, was all developed after we had built this particular plant. Now, Calendria tube, pressure tube to be cut and removed, Calendria to be cut and removed are very difficult job, because they are very highly active. And before that one fuel, if the fuel has come out somehow, and then and this has happened also, fuel has come out, and then this has to be still isolated and taken out the fuel. One of the very major failure which we saw was the uh, you know uh, this pressure tube of Rajasthan 1, Rajasthan 2, Madras 1, Madras 2, Kapra 1. These are the reactor with zircaloy 2 pressure tubes were there. And we learned from Canada that this particular pressure tube, there was one catastrophic failure, very long rupture, about 2 meter long rupture has taken place. We had very little information about it. We developed all this. We found out how the blisters are formed ultimately and gets aligned, which can end up in this type of crack, and how hydrogen migration takes place. So we study that one. Then how to develop tools and flask, and to take out these things. Also take out calendar to wherever required. Do inspection in such high radiation areas and go ahead. But hats off to all my seniors, hats off to my colleagues who have been in a position to successful and do this all this maintenance. We have never stopped. In Rajasthan Unit 1, we kept on operating, and besides the recent decision, nowhere we stop. Madras Atomic Power Station, we are running. All of the reactors we are running without any difficulty. So despite any difficulty, and that's what capability has to lie. And industrial support was there, R&D support was there. We succeeded. Okay.
Absolutely, sir. You're right. I mean, without team effort and I mean, yes, hiccups and failures are a part of a mission and something which is at such a large scale. But yes, that's true. I mean, team effort is definitely the key to success. Um,
Vaishnavi, I must say that, yeah, failure should be ideally conceived in advance, But if it has happened, we should have capability of handling it. And third thing is there, if a failure has taken place, do not repeat the mistake. And that's what
Absolutely.
we have followed this particular principle.
Absolutely. Well, so you said something about nuclear embargo, which was imposed on India. Could you maybe tell us a bit more in detail about what it was and how it affected us, our power program and our journey in overall?
Well, it was total embargo in 1974. No knowledge, no equipment, no technology sharing, do of your own completely. And that's how actually we did it. Self, and that helped us self-reliant. India was the only country in almost 80 which was almost doing everything of own, 100% of its own. See, the closed fuel cycle, everything element which was there in place. Uranium, the pre-reactor, that is, uranium exploration, mining, and converting, fuel fabrication, then reactor construction, then reactor operation and maintenance, take out fuel, give it to somebody else to separate it, waste, high level waste, low level waste, take out plutonium, and make again fuel and put back in the reactor. Fuel cycle was closed by India and completely of their own. Nobody in the world was in a position to do it. So I must say, embargo brought lots of benefit to us and lots of knowledge increased and capabilities increased within country.
Thank you, sir. Well, India is currently entering, or let's say it has entered its second stage of nuclear power program, which is actually the fast reactor technology. So I would like you to give our viewers some details about what this fast reactor program is and how does the adoption of second stage overall boosts the India's nuclear energy program.
Yes. See, as I said, fast reactor is the backbone of India's nuclear power program. We can produce a limited amount of maybe 63,000 megawatt or so, and with the imported produce more reactor with our own fuel, 63,000 megawatt power. But that's not all. First, we have to convert thorium as a useful fuel by making it fissile, uranium-233. Now, this technology is altogether different. When I came from the NPCIL and working here, everything was different. It is a pool type of reactor. It is very, very large. Every equipment is humongous. For example, a pump, an 11-meter long shaft, steam generator here is 30-meter long steam generator. Then if you say sodium to air heat exchanger, they're so big that we took 8 months time to shift from Walchan and Nagar Industries to Kalpakam. This humongous equipment, sodium as a fuel, as a coolant, and sodium as a coolant is sodium. If a drop comes out, you are aware it will not tolerate any moisture in the air and it will burn. So we had to handle 1,850 tons of sodium that was brought in 90 consignments, and then not a drop. We are the only country which brought this particular sodium and put it and ultimate safely with us without a drop coming out. And in a 90 consignment over 2.5 years time. We were, of course, we faced tsunami right in the beginning and massive tsunami, and everything which was in the plant that was destroyed. Incidentally, it was initial stage of the plant and civil works was going on, but nothing was left with us. And the question came whether this is the right place. And then we called experts throughout in India, and they deliberated and ultimately gave us some recommendation with increased height of the platform, and then on so that water cannot enter, and we kept on continuing our program. So we had difficulties and we had challenges, but this reactor was built with the very high quality. Both industries participated very well in that one. But of course, during commissioning stage, some new issues arose. Of course, I was out of picture by the time because I had retired and joined ITER by that time. But I know that they are handling very effectively despite all this trouble which they have faced in some of the equipment. Now, MOX fuel is new, fuel handling mechanism is new, coolant is new, size of the equipment is new, handling methods are new, quality assurance program is very stringent. So with so many new things, where was the experience? The experience came from fast breeder test reactor, which had operated by the time more than 25 years very successful. And they had developed this maintenance capabilities. They had studied how this reactor behaves, how the fuel behaves. Of course, fuel is different in FBTR and fuel is different in PBR, but how to locate a failed fuel and everything, all the information which was needed, and post-radiation examination of some of the parts coming out from the reactor, they reveal lots of things, and that makes the fast breeder program very robust. I must say, it has been developed on very strong grounds and by very capable team. And I'm very sure very soon we are going to see a day when PBR is successfully operating and we are accelerating our second stage of nuclear power program.
Absolutely, sir. I mean, I think that's the one thing we are all waiting for. And in fact, even I, during my master's, I had the opportunity to visit IGCAR, the facility, and we had special visits to the FBTR facility. So, I mean, if the test reactor itself, seeing the scale of all the test facilities and how everything was planned, I'm pretty sure the actual construction of PFBR was much more required a lot of details and intricacies than what we saw in the fast breeder test reactor, for sure. Well, you mentioned ITER just in your last answer, and as we know that the ITER organization is a participation of 7 key members, and India is a part of this group, this elite group. And apart from the the unique scientific collaboration that it represents, and the shared goal of having green and clean energy, what do you think is the major takeaway for India to be a participant in this ITER program?
Okay, from that better before going to takeaway, I must say that this is very heartening that almost half of the globe, people from half of the globe, they are involved in this particular ITER program. And to coordinate all this effort is a task which has been successfully done by the ITER. And this is really commendable. Bring people to common mode of thinking, common program, common schedule, common method of working. This is all a challenge which has been very successfully established. Everybody used to make their own methods. For example, Russia works on the gold standard. The European, that is, American work on ASME standard. India works on various mixed standards. Some of them are German standards, some of them Russian standards, some of them are American standards, etc., etc. Still, you make equipment, integrate all of them was a challenge, again, very successfully met. Everybody has gone together very well. Now, your question emerging from that one is, what was the question, second part of the question? Can you repeat your question, please?
What would be the major takeaway for India as a participant in the ITER technology?
Well, India is participating as equal partner. So India is spending 9% of the money, and India is beneficiary of the 100% technological development which has been done. So one of the greatest advantage to India is by spending lesser money, get much more in return. The people are getting trained. Lots of Indian today, if you see, many industries are also put people as IPAs. So they are learning all this international practice. But I must tell you, Vaishnavi, Indians are second to none. I'm finding, on the contrary, Indians are better in many, many ways to many other people. First of all, Indian can work a lot. An Indian can work very systematically, and they are very methodical. They have got capability of handling software, and they are wonderful fellows. They are very cooperative. They never argue, but still keep on going as a team and believe here as a team effort. I wish in India also we make a better team. But our big takeaway is all the technological development which is taking place in the form of material, in the form of sciences, which is associated with the tokamak. And see, this is all we are getting advantage of this technologies right now. When it comes to DT phase, when it is ready for demo reactor, when India may definitely participate. And as many Indians and Dr. Kakotkar has said that we would like to make a demo in India. I wish this happens one day. But before that one also, see all this technological development which is taking place where Indians are participating. All technologies are coming back to India, and capabilities are coming back to India. And we have our industries also got software advantage. The cryostat, which is the largest equipment vacuum vessel of the world, that has been made by Indian industries. Cryo system, which is one of the largest cryo system ever made in the world. India has major participation on that one. The electrical systems, ECR, ECS system, etc. India has very major significant role to play. Very large cooling system which has been built here, all with Indian support. Rather, this when electromechanical work started in this ITER, it was all Indian work, and it has been seen by various huge number of people and appreciated Indian capabilities.
Thank you, sir. Thank you. And could you maybe inform us a bit more about the main features of ITER facility to our viewers, and also how over the years, because I think the ITER project itself has taken over 30 years now. It's going to 30 or 25 years, if I'm correct. And could you highlight some of the major attainments that this project has had so far?
Vaishnavi, this is not 30 years, but leave that on aside. The project, of course, has a new date, and project is adhering to the new date of first plasma in 2025 and DT operation in 2036. Now, this was decided in 2016 by ITER Council, and that time I was in ITER, and we are going ahead strictly on this particular date, and it's fascinating to see how this every milestone is being met. Now, strategically, ITER is placed next to CA, and that is very great advantage. That this many facilities and development expertise which is there in CA that can be easily obtained, and the land has come from CA, and in how that not much effort had to be done in infrastructure development. This reactor is a very strange. When I came here and saw the size of the equipment, I was only thinking PFBR, which has built the biggest equipment for India. Here, the cryostat, 30-meter diameter vessel. Oh, so almost same height, 20 meter height. So, and this is so many port cells which are there, they're opening for the port cell. So this was such a complex construction. See, material construction without fabrication, without need of excessive repair. Then is handling, transportation, cleanliness, and installation. This big cryostat base has been installed. It requires 1,500 ton crane to lift 1,250 ton equipment. It is 30-meter diameter. It was very fascinating to see such a large equipment being lifted and placed. It has never happened anywhere in the world that this type of fabrication has been done. and this has to be done in 2 stages. Larsen Toubro was responsible to fabricate it. They fabricated some of the portions there at their end and brought here to integrate, and they integrated here. So this. What I'm trying to say, Indian industries have also played a very major role. It has got very, very large equipment. It has got several new technology. It has got very extensive requirement for diagnostic systems. It has got very elaborate electrical system. It has got very, very, very large magnet. People would have never seen this type of magnet. The and all the electrical backup which has to be there. The cryo system, the vacuum system. It has a 4-degree Kelvin. Such a large volume has to be brought to 4-degree Kelvin. Vacuum vessel, which is such a huge complex equipment, and which will be at that vacuum, and ultimately is being built, of course, by various parties in the world, and it includes European Union and also includes that Korea, and magnets, which has been Russia, which has been in Japan. It is all collaborative effort. The cooling system, and it is very important to have a cooling system. See, we should see to it that no failure takes place later, because the failure here is going to be very, very difficult. So again, this is a technology which requires a different thinking, different material, different processes, and collaborative effort to make success. Extensive discussions take place here, and then only we proceed. And I think finest experts of the world, they have been working in ITER, and of course the leader today, Director General, is wonderful.
Thank you, sir. I really hope we see the future soon of about ITER project as soon as possible. And I'm really sorry for misinformation on my part regarding the years. Well, if I compare the nuclear fission reactor technologies and the fusion reactor technologies, so we know there's one thing which is like very, people are very strict or very afraid about one word in particular, which is radiation leak and safety, nuclear safety, when it comes to fission reactors. So, since fusion is also a part of nuclear energy, can you maybe tell us how this safety aspect is firstly different in fusion reactors, and secondly, how is it being accounted for in a facility as big as ITER?
Okay, so first of all, Vaishnavi, I must say that India has not released any radioactivity outside. India has not met any accident, and its safety records is excellent. Excellent. And we all Indians should feel proud of it, how we have done. In thermal reactor, the biggest issue which is there is the fission products. The fission products, many of them are very long lived. And second issue which is there, the delayed neutron, which keeps on producing heat in the fuel for a long time, even if you have shut down the reactor. And if you are not in a position to cool, then it can give you difficulties. But there are lots of engineering has been done to ensure, for example, pressurized heavy water reactor, if I take, the first containment for the fuel is fuel itself, that will not allow many of the isotopes to go out. Then primary heat transport boundary, that will retain even if fuel has failed. Third thing is that we have got the containment, and we have got exclusion radius, and we have exclusion radius of 1 kilometer. So people will not get exposed, and we maintain the reactor in vacuum so that outside environment come inside the reactor building. Well, as far as thermal reactors concerned, or fast reactors concerned, safety has been very well addressed in India, and it has been pursued, and we never had a release. But as far as ITER is concerned, when I came here and studied, it was very fascinating, because here it is so easy. You stop fuel and this reactor stops. So it is as simple as that one. There is no issue of fission products. There are no fission products, and there is no issue, at least of delay neutron. But still, there are some issues are there because there is tritium, and tritium has almost 12.5 years half-life, to be precise 12.3 years half-life, and tritium should not come out. It's a beta emitter, and it should not come out, and it should be contained. And once tritium has to be contained, we have to have all provisions to see that tritium does not come out. So tritium will be retained in the vacuum vessel itself. And even if it comes out, for whatever reason, the containment boundary is there again, uh, uh, which uh, which will not prevent, and it is designed for 1 bar pressure. It will not allow the radiation to come out or tritium to come out. Here, this activity level for the general public during operation phase of ITER is 1,000th of radiation you get from the environment if you are living close to the anywhere else also. 1,000th. So it is very low, almost for all purpose. And even during accident, even if worse accidents take place, also there will not be any need for evacuation. Nobody will be required to evacuate the site. In India, that the biggest fear is people evacuation and exclusion zone because of the fission products there. But ITER, there is no such issue. That means ITER type of reactor can be installed in any populated area in future. Once this is done, ITER is done, and we go for demo, we can go to even populated areas also. It will be very safe reactor. And there, of course, detritiation facility, etc., where tritium is handled, and we have got all provisions so that tritium does not come out. So it's very robust reactor from the safety point of view. It should be a choice. When there are various energy options are available, it should be a choice, simply because of the very strong safety, safety philosophy and very little safety concern.
Thank you, sir. Thank you so much. So now I move on to the last question that I have, and it is actually not related to any of the nuclear technologies or any particular technology in particular. It's not a question about any reactor technology, but it's more of an advice that you would like to give to maybe the young professionals who are currently in the nuclear industry or maybe are thinking of joining the nuclear industry.
Thank you, Vaishnavi. Thanks. This question should be asked by every young person. Yes, why I should choose nuclear as a career. So I will think from my own perspective at what I gained by joining nuclear, and if I had for energy production, and what if I had joined somewhere else. First of all, I have lived with a very highly knowledgeable people, scientifically oriented, logical thinking, safety oriented, going for details and intricacies. First of all, your environment. So your environment is going to be excellent if you are with the nuclear industry. Second, you have got capability of working in any of the field of the nuclear technology, or I must say technology. You may want to be with construction, you can be with construction. You want to be with design, you can be with design. You want to be electrical, you can be with electrical system. You want to pursue any R&D in your areas of choice. Well, you are sorry. So you can do in your area of interest. You want to file patent tomorrow, you have ample opportunity of filing patent. You want to work in a good lab, you want to have lots of machinery equipment, lab equipment, etc. You want people to advise you, want to do research, multiple research. You can do anything if you are with the nuclear industry. You want to be in the industrial sector, you can go to industrial sector, is still participate with that one. See, opportunities are ample, and you will find yourself tomorrow giving lectures at various places, invitee at many places. You will find people will seek your advice, will like to meet you. This is all advantages. If you are sincere in your job, you can always get. Growth is enormous. You can reach any level. If you have joined as a young engineer, you can still go to chairman atomic energy commission level. They're all came to that level or whatever other senior levels in Department of Atomic Energy by your own skills. I have seen any favoritism done any time by anybody, any senior in this department. They all gave equal opportunities and they will always recognize capabilities. There are various options of department using Department of Atomic Energy. Of course, training school is one of the best, but you have many other avenues also from one can enter. But enter and explore, and you see if you don't like, you leave it. But I don't think that many people leave. Once they enter nuclear, they become nuclear professionals. Uh, join it. Join it. This is a wonderful career, I must say, from my own experience. Thank you.
That's Thank you, sir. That's absolutely true. In fact, I mean, when I started my masters in nuclear, I wasn't really sure. But 3 years after that, I found myself doing the PhD, and I'm still in the field and excited about it. So I'm pretty sure, after hearing what you've said, there'll be a lot more students and young people who would want to and who would really wish to enter this field. Thank you so much. Well, this brings us to the end of today's session. Thank you so much for giving us such wonderful answers to questions. I mean, I'm I did not know a lot of things myself, so it was a really enlightening experience for me, and I'm sure it was an enlightening experience for our viewers as well. And have a very good evening, and thank you,
Thank,
everybody. Thank you, our
thank
viewers.
you. Thank you very much, Vaishnavi, and thank you, all of you, for propagating the message of nuclear to the young generation.